I'm Norik, I'm from Beijing.
Hi, I'm Milan, I'm from Brighton.
Hi, I'm Amina and I'm from South London. We're all third year University of Manchester chemistry students, and this is an NMR spectrometer. So NMR has various applications in the real world. One of these applications is within magnetic resonance imaging, which is used within the medical industry. Essentially, that just looks at how tissues in the body interact with water. Another application is within the world of sports. So you have the World Anti-Doping Agency, which regularly carry out anti-doping tests. They do this, they are taking samples from athletes, so maybe blood, urine, or both, and using NMR, they look for sports-enhancing drugs to see if the athlete has been taking these. A famous example is Maria Sharapova, who was found to be taking meldonium, and she was not able to participate in the Australian Open in 2016.
At A level you learn about carbon and hydrogen NMR, but there are lots of other nuclei that you can use. With carbon NMR, you use 13 carbon NMR. This is because for NMR you need an odd number of protons, neutrons, or both. Carbon 12, which is the normal atomic mass of carbon, has 6 protons and 6 neutrons. However, carbon 13 has 6 protons and 7 neutrons, which means that it has an odd number of neutrons, giving it spin value.
Nuclei are electrically charged and have spin, which causes them to behave a bit like a magnet. In NMR, nuclei are exposed to an external magnetic field. The nuclei then can either align with this external magnetic field or align against the external magnetic field. This is how a signal is produced.
We're next to the spectrometer. You are not allowed to bring with your wallet, mobile phone, or keys inside your pocket, as it will interact with the spectrometer. Superconducting magnets is cooled by liquid helium or liquid nitrogen.
Two important requirements for an NMR solvent is that the solvent is deuterated, which means that there's no hydrogen atoms in there and all hydrogen atoms are replaced by an isotope of hydrogen, deuterium. Another important requirement for an NMR solvent is that if your sample is a solid, the solvent must be able to dissolve the solid, but also the sample could be a liquid.
in the NMR spectrometer, we then need to analyse the spectra. And as an undergraduate, we use the software Mestranova, which basically allows us to utilise a few of its functions, such as peak picking, integration, and baseline correction. So once you get the result from the NMR spectrometer, after the sample has been run, we get the spectra emailed to us in the format of a zip file. We would then download the zip file and open it in the software that is called Mestranova, which will allow us to carry out all the analysis. So the first thing we'd probably do is look to do the peak picking, which basically just assigns all the different peaks and distinguishes between them. So you would click the analysis button and there's the option to do automatic peak picking. You could also manually do it, but most of the time we just use the automatic function, and then maybe if it didn't pick up on certain things or it labeled things wrongly, we then manually peak pick, and you can zoom in and zoom out and all of that stuff. The second thing we'd probably do is integration. So we want to know the area under the peak. That is also within the analysis function. You just scroll down and it auto-detects the different regions. The final thing, but what I would say is probably one of the most important, is the baseline correction. Baseline correction basically gets rid of a lot of the noise of the spectra, which is all the little squiggly lines that you would see on the initial raw spectra we get. So if you go into processing, you can use the baseline function and it basically gets rid of a lot of the noise. We'd probably do a few final checks and go over it and maybe compare it to known spectra to see if it kind of matches up with what we are looking for. But that is essentially how you would carry out an analysis of a spectra using Mestranova. In proton NMR, it's basically the study of the different hydrogen environments in a molecule. If it was carbon-13 NMR, you'd be studying the different carbon environments in a molecule. This is propan-1-ol. As you can see, all the hydrogens attached to this one carbon, they are all chemically equivalent. We would say that this is one hydrogen environment. This is another hydrogen environment. This is another. And the hydrogen bonded to the oxygen is another hydrogen environment. The different chemical shifts that you get for the different hydrogen environments depends on its proximity to the electron withdrawing group. The electron withdrawing group in propan-1-ol is the oxygen, or I should say, the OH group, the alcohol group. The hydrogens on this carbon are closest to the alcohol group. This then means it is the most de-shielded, which basically means it has the highest chemical shift out of all the other hydrogen environments. As you move further along, this would then have the next highest chemical shift, this hydrogen environment. And then lastly, the one that is furthest away from the alcohol group would have the lowest chemical shift. So in NMR, you are able to look at the number of hydrogens in a molecule or in the different environments by looking at the integration of a peak, which basically just means the area under the peak. So for this carbon that has 3 hydrogens attached, you may get an integration of 3. For this hydrogen environment here, where you have 2 protons attached to the carbon, you may get an integration of 2. But integration is not definitive, it is a ratio. So that means whatever number you get is relative. So you could get an integration of 3 and 2, or you could have an equivalent ratio, such as if you multiplied that ratio by 2, you would have 6, and 4. So remember, integration is not definitive, it is a ratio.
The third important feature of a spectra is the splitting, or the amount each peak is split by in an NMR spectrum. This only happens in hydrogen NMR, doesn't occur in carbon NMR. So splitting is the idea that a peak in an NMR spectrum is split into lots of different smaller subpeaks, and these subpeaks are relative to the number of hydrogens on the adjacent carbon atom or the carbon atom next door to the other carbon atom. So for example, if you look at the peak of this hydrogen environment, you can see that the adjacent carbon has 2 hydrogens on it. This means it will be split into a triplet according to the n+1 rule, as the n+1 rule states that the number of subpeaks in the environment is equal to the number of adjacent hydrogen atoms plus 1.
So during A-levels, we're taught that TMS is used as a reference peak in terms of the chemical shift.
In reality, this is not really necessary in a real life lab situation. Another myth is that CCl4 is sometimes used as a solvent in NMR. However, it's actually very, very rarely used, as CCl4 is highly carcinogenic and toxic.